Hello everyone, my name is Charlie, aka Anderson. Today I will go over the AP Physics C, Electricity and Magnetism 2017 exam. I will walk through that exam. Now the link to that exam is in the description, the PDF of the exam. The purpose of the session is to help you prepare for the exam, and also timestamps are given for those who need it. So here are my qualifications in terms of scores, SAT and AP scores, and I'm also a certified tutor through schoolhouse.world, which is this online tutoring platform. You can see there's a link in the description that leads to my tutoring transcript. Why did I decide to make this video? I know that studied resource videos aren't the type of video I usually post, because I usually post memes and gaming, but I decided to make this just because why not, I guess. Anyway, so without further ado, let's get into the formula sheet. Here's the AP Physics C formula sheet. This formula sheet will be given to you when you take the AP Physics C Electricity and Magnetism exam. It will also be given to you when you take the AP Physics C Mechanics exam, and it also includes many constants and unit symbols and all that good stuff. Most likely you wouldn't really need to use much of this, but like it would definitely be helpful. I'm sure it will be. Anyways, without further ado, let's get into the first question. So I'm going to give you 20 seconds to read over the questions 1 and 2 and the questions, and then I'll go over the answer then. Anyway, so 20 seconds have passed, so I'll go over the answer. Now for question A, for question 1, it asks for the sign of the the work done by the external force and the work done by the electric force. So if you remember from AP Physics C Mechanics, work is equal to the force, to the integral of force with respect to distance traveled. Now, basically what that means is that if the displacement of the object has the same direction as the force, then it's positive work. If the displacement of the object has the opposite direction as the force, then it's negative work. So the answer to question 1 is B, because the external force has the direction of the external force is the same as the direction of the displacement of the object, and and for the electric force it's the opposite. So that's why the answer to question 1 is B. Now for question 2, it asks about the relationship between the electric potentials at the 2 points 1 and 2. Now the electric potential is equal to the charges, to all of the nearby charges over their distance from the point. It's equal to the charge over distance and of all of the nearby charges, and then like you add them together. And all that multiplied by the constant, the 1 over 4 pi epsilon, which is also written as k. But in the context of this question, it doesn't really matter. It just, in the context of this question, all that there is are 2 points, 2 charges, and for point 1, 2 positive charges. And point 1 has a greater distance from the 2 positive charges than point 2. Since point 1 has a greater distance to the 2 positive charges, then its electric potential must be lower, because all of the relevant charges are positive and the point 1 is at a greater distance. So yeah, its electric potential is lower. So the answer to question 2 is A. Now questions 3 and 4, again, I'll give you 20 seconds to read over them, and then I'll go over the answer. Okay, so now question 3 asks about the electric flux through sphere A. Now keep in mind, electric flux isn't the same as magnetic flux. Many people get electric and magnetic flux confused. So electric flux is just how much electric field, how much electric field penetrates the point. So like, how do I say this? So like, it's basically like, so in the context of this problem, there's a sphere and electric field. The electric field is going through the sphere. So in the context of this problem, the electric flux is just the electric field. The electric field times the surface area of the sphere. In the context of this problem, that's electric flux. Now, the electric field can be written as K times Q over R squared, Q being the charge. That's another way to write electric field. So electric flux of these two spheres is electric field times the surface area of the sphere. Now the surface area of a sphere is a 4 pi r squared, and the electric field that penetrates the spheres are kq over r squared. And if you look at this expression, you'll see that the r squared here and here cancel out, so you end up getting kq 4 pi. So now the only thing that so these spheres are identical except for the radius. The radius is the only thing that makes these two spheres different. So however, since the radius doesn't matter in the final expression, that means that the electric flux going through these two spheres must be the same. So the answer is C, 1 over 1. That's the ratio. Now the electric field, on the other hand, is kq over r squared. Since the radius of the second sphere is 2 times. Since the radius of the second sphere is twice the radius of the first sphere, that means the electric field, the magnitude of the electric field going through the second sphere must be 1/4 the magnitude of the electric field going through the first sphere, because it's a something over r squared. The difference between the radius is like sphere B has twice as much radius, so over 2r squared, that would be over 2 squared, that would be something over 2 squared, that would be 1/4 that. So the ratio between EA and EB is 4 over 1, because the EA, the electric field going through sphere A, is 4 times as strong as that of a sphere B. So the answer to question 4 is A, 4 over 1. Now question 5 asks which of the following figures shows 3 identical capacitors connected to a battery, each of the following figures shows 3 identical capacitors connected to a battery. Which arrangement has the greatest equivalent capacitance? So it's given to you on the formula sheet, as well as I'm gonna tell you. So CP is equal to C1 plus C2 and all of the capacitors. And oh yeah, I just realized what I said could be misinterpreted. What CP means is the equivalent capacitance. Well, okay, in the context of this problem, C sub P means equivalent capacitance for parallel capacitors. The P stands for parallel, so the equivalent capacitance for capacitors in parallel is equal to the capacitance of the capacitors added together, equals the capacitance of each capacitor added together. Now C sub S, the S stands for series. For capacitors in series, their equivalent capacitance is equivalent to 1 over the first capacitance plus 1 over the second. Like you get a point, right? So now when it comes to parallel and series capacitors, it's always true that 2 capacitors in parallel have greater equivalent resistance than if the 2 capacitors were in series. Because if you solve this, you'll see that no matter what the capacitance of the 2 capacitors are, placing the 2 capacitors in parallel would always result in a greater equivalent capacitance than if they were in series. So answer E is the correct answer, because the three capacitors are all in parallel, so they must have the greatest equivalent capacitance. For capacitors A, B, C, and D, some of them for answers A, B, C, and D, there's two capacitors in series, and answer choice E is the only one where they're all in parallel. So answer E is the correct answer. Now, question 6 talks about a copper wire of length L and diameter D that dissipates energy at a rate P0 when the current in the wire is 10 amps. A second copper wire of length L has diameter 2D. What current in the second wire would dissipate energy at the same rate? So this uses the power equation. So P equals IV. A good way to remember this is that the Ivy League schools have a lot of power, so which translates to, in this scenario, P equals IV. Now, since V equals IR, voltage equals current times resistance, you can write this as P equals I squared R. And what is R? Well, R is the resistance. R is resistance of a wire. Now the resistance of a wire is equivalent to rho L over A. Now the two wires are both made of copper, so they have the same rho. Rho is just the resistivity of the material. Since they're the same material, they have the same rho. And they also have the same length. So the rho and the L, you can just like ignore that because they're the same for both. However, they have different areas. Now the second wire has a diameter of 2D, while the first wire has a diameter of D. Now since the second wire has a diameter twice as long as the first wire, and since the area of a circle is pi r squared, or pi times diameter over 2, that's squared. Basically, since the second copper wire has a diameter that is twice as large, it has a radius that is twice as large, so therefore it has an area that is 2 squared times as large. So it has an area, so copper wire 2 has an area of that is 4 times greater than copper wire 1. Therefore, its resistance must be a quarter the amount of the resistance of the first copper wire. This is because it's 1 over area, and since copper wire 2 has 4 times the area, then it has a quarter the resistance. Now, therefore, the answer must be D, and the reason why is because since the resistance is a quarter the amount, since the resistance is only 1/4 the amount, then the current has to be twice the amount in order for P to remain constant, because like as it says, the rate P is the same for both wires. So since resistance is 1/4 the amount, then current has to be twice the amount in order for P to remain constant. So the answer is 10 times 2, 10 amps times 2, which is 20 amps, which is D. The answer to question 6 is D. Now I'll give you 20 seconds to read through question 7, and then I'll go over the answer. Oh, by the way, just so you know, if you ever feel like 20 seconds isn't enough, which it definitely which is definitely possible, if you ever feel like 20 seconds isn't enough, you can always pause the video, you know. Anyways, so what is the new time if the original inductor is replaced with an inductor of inductance 2L? Well, since the inductance doubles, therefore the time also has to double. So the answer to question 7 is B. Now question 8, I'll give you 20 seconds to read through this and I'll go over the answer. Alright, so Basically, the equation for EMF induced, the equation for induced EMF is the induced EMF is the integral of the of the electric field. I mean, sorry, it should be of the of the electric of this the integral of E dot dl. Now and keep in mind this is given to you on the formula sheet. On the formula sheet it says that induced EMF is also equal to negative d electric flux or d magnetic flux over dt. So the derivative of the magnetic flux with respect to time. And magnetic flux, it's also given to you on the formula sheet. On the formula sheet it says magnetic flux is equal to the integral of the magnetic field with respect to area. Now, the magnetic field is uniform, meaning that it's the same and it's not changing. So magnetic field is the same. So therefore, the only thing that matters that would induce EMF would be if the area changes, the area with respect to the magnetic field. Now, so therefore A is not correct, B is not correct, C is not correct, D is not correct, because like for A, B, C, and D, the area doesn't change. Like the area of the loop of wire with respect, the area perpendicular to the magnetic field stays the same for A, B, C, and D. So since the area of the loop with respect, since the area of the loop that is perpendicular to the field stays the same, that means there cannot be any induced EMF. So the answer is E. An EMF cannot be induced in the loop without changing its orientation relative to the magnetic field. And basically what that means is changing the orientation of the loop would change the area that is perpendicular to the magnetic field. So yeah, so the answer is E. Question 9, I'll give you 20 seconds to read over it and then I'll go over the answer. Alright, so now it's just asking you if the velocity is doubled and the magnetic field strength is reduced by half, then the power dissipated would be what? Well, basically what's going on is that the magnetic field, there's a magnetic field that is inducing an EMF. There's induced EMF here, and okay, let me first start with power equals current times voltage. P equals IV. I've given you the mnemonic already. P equals IV, and the IV in this case is just whatever the induced EMF is. Like the IV is perpendicular, is proportional to the induced EMF. An induced EMF is the derivative with respect to time of the magnetic flux. And the magnetic flux is equal, it's on the formula sheet, the magnetic flux is equal to the derivative of the magnetic field with respect to the area that is perpendicular to the magnetic field. And the area is equal to the length times the height. Now height stays the same, but the length is increasing by v. The length is increasing by v of t. Now here's the thing. So v of t is doubled. The velocity is doubled. However, the magnetic field strength is halved. Now so when velocity is doubled, the induced EMF is also doubled. But then, since the magnetic field strength is reduced by half, then the induced EMF is also reduced by half. So the power dissipated in the rod stays the same. So the answer is C, P. The answer is C, which is P. Yeah, that's what I meant. Question 10, I'll give you 20 seconds to read over it, and then I'll go over the answer. Anyway, so now first we can go over Kirchhoff's loop rule. The Kirchhoff's loop rule is that in a loop the total change in voltage has to stay the same, has to be 0. And since the battery stays the same, that means the total change in voltage across the 3 capacitors have to stay the same. Remember that since the battery's voltage stays the same, then the total voltage across the 3 capacitors have to stay the same. Across the 3 capacitors combined. Now is constant. Now the capacitance of a capacitor is K epsilon naught A over D. Now A and D stay the same. Epsilon naught is a constant as well. So K is the only thing that is changing. Now since K is greater than 1 before, and afterward K just becomes 1. Like after the dielectric is removed, K becomes 1. So K goes from greater than 1 down to 1. So therefore the whole expression here is decrease. So the capacitance decreases after removing the dielectric. And since Q equals CV, Q equals capacitance times the voltage. Now, of course, so since the capacitance goes down, what that means, since the capacitance of capacitor Z goes down, the voltage has to go up to account for the decreased capacitance. And keep in mind that Q could also change, like Q is the charge, which could also change, but the amount with which Q changes is irrelevant because it doesn't impact the answer to this question. Now, since the voltage across capacitor Z has to increase, then the voltage across the other 2 capacitors have to decrease, so that the voltage across all the capacitors stays the same, because like we have to follow Kirchhoff's loop rule. So therefore the answer is E. Now for questions 11 and 12, again I'll give you 20 seconds to read over them. I'm back. Alright, so now basically this is just really a concept question. Now when the slab is inserted, so like the slab is inserted and the dielectric constant of the slab is greater than 1. So since the K is greater than 1, that means when the dielectric is inserted, the capacitance has to increase. The charge goes up, but the voltage remains constant. So therefore the answer to question 11 is A. The charge increases, but the potential difference, the voltage, remains the same. And the reason why the voltage remains the same is because it's a closed loop. So the voltage has to remain the same because of, again, Kirchhoff's loop rule. Now, if the switch were open, then the charge would remain constant. This is just a concept you have to memorize. When the switch is open, the charge remains constant. So since the charge remains constant, since Q is constant, and since C increases, therefore, since Q is constant, and since C increased, therefore V has to decrease. Because, since C increased, then V has to decrease to account for the increase in capacitance. So, therefore, the charge remains the same, and the capacitance increases. So the answer to question 12 is C. I hope that helped explain this to you. C increases, and I mean, yeah. So, yeah. Anyway, question 13, I'll give you 20 seconds to read over this question and try to solve it, and then I'll go over the answer. Alright, so now this requires you to understand the right-hand rule. There are actually two right-hand rules to magnetic force and two magnetic fields and their magnetic force. So it's known as the right-hand rule. Basically, for the right-hand rule, it states that, well, for one, you need to know the magnetic field that passes through wire A. So whenever there's a current flowing through a wire, you would point your thumb, the thumb of your right hand, in the direction of the current, and then the direction with which your fingers curl would be the direction of the magnetic field. So this equation demonstrates the right-hand rule. So as the current goes up, if the current goes in this direction, then the magnetic field has to go in this direction, in a circle around the current. So for the magnetic field of this circle, if you take your right hand and point your thumb out of the page, and then you'll see that your fingers would curl in this direction, like your fingers would curl like this. So therefore there would be a magnetic field going in this direction, and right here the magnetic field would go in this direction. And with this current, you also do the right-hand curl rule, and you'll see that the magnetic field would go in this circle, in this direction, and therefore the magnetic field would hit wire A in this direction. Now the two magnetic fields would add together, and when you add together the two magnetic fields at wire A, you'll get a magnetic field pointing up. So now you need to use the other right-hand rule to know the magnetic force. Excuse me, sorry about that. So the magnetic force is perpendicular to the plane created by the current and the magnetic field. And you use this right-hand rule. So your thumb would be the current. Yeah, your thumb would be the direction of the current. Your fingers would be the direction of the magnetic field, and your palm would be the direction of the magnetic force. So if you take your right hand and you do this, and you point your thumb in the direction of the current, point your fingers in the direction of the magnetic field, then your palm would point in what direction? Well, the answer is E, towards the right. So I hope this explains it pretty well. Yeah. Question 14, a beam of particles travels at a right angle to a uniform magnetic field. Particles can be separated into different trajectories based on which of the following properties? So the answer is E, which is all of them. And the reason why is because, well, because the magnetic force is equivalent to the charge times velocity cross magnetic field. Now, so here the force is equal to this, and force is also equal to mass times acceleration. So let's find the acceleration. Well, the acceleration due to the magnetic force is equivalent to the magnetic force over mass of the particle. So therefore the answer is E, because all three of them, changing any three of these quantities would change the trajectory. So changing the charge of the particle would change the acceleration, which would change the trajectory. Changing the mass of the particle would also change the acceleration, which would also change the trajectory. And same goes with velocity. So the answer is E to question 14. Now question 15 may seem hard, but really it's not that complicated. There are just 6 2-ohm resistors connected to the 12-volt battery as shown in the figure above. What is the current in the resistor labeled R? So first you need to find the equivalent resistance of the whole circuit. In order to find the equivalent resistance of the whole circuit, you can do this. So now first you know that resistors 1 and 2 are in series. So resistors are the opposite to capacitors in the sense that if 2 resistors are in series, then you add their resistances together, and that is their equivalent resistance. If 2 resistors are in parallel, you do 1 over first resistance plus 1 over second resistance, like in this equation. Anyway, so first let's first give assign numbers to the resistors, resistor 1, 2, 3, 4, and 5. Now resistors 1 and 2 are in series, so let's find the equivalent resistance of these two resistors, that is 4 ohms. Now resistors 1, 2, and 3, so resistors 1 and 2, let's just call that resistor 1, 2. Resistor 1, 2 is in parallel with resistor 3, so the equivalent resistance of resistors 1, 2, and 3 would be 1 over 4 plus 1 over 2, and that would be 4 over 3. Now resistors 1, 2, and 3 are in series with resistor 4, so to find their equivalent resistance you do 4 over 3 plus 2, 4 over 3 being the resistance of resistors 1, 2, and 3. So and then you know that, and then you would look at this and you'll see that resistors 1, 2, 3, and 4 are in parallel with resistor 5, as in like the current can travel through resistor 5 or through resistors 1, 2, 3, and 4. So then, since they are in parallel, you take their equivalent resistance using this equation, and you could plug it into the calculator. Keep in mind that calculators are allowed during the exam. So therefore you find that the therefore you find that the equivalent resistance of all of the resistors is 1.25. Oh wait, sorry. The equivalent resistance of resistors 1, 2, 3, 4, and 5 is 1.25. And then you take resistor R, this resistor, and then you take resistor R and you add them together, because resistors 1, 2, 3, 4, and 5 are in series with resistor R. So you add them together and you get the equivalent resistance of all of the resistors combined is 3.25. Now we know that I equals V over R. It's given to you on the formula sheet. Current is equal to voltage over resistance. You know the voltage is 12 and you know the resistance is 3.25, so the current is 12 over 3.25, which is 3.7, and that's how the answer is B. I'll give you 20 seconds to read over this and I'll go over the answer. So, basically, the reason why the answer is C is because, so, for one, an ideal voltmeter has infinite resistance. Of course, it's impossible for something to have literally infinite resistance, but like, the ideal voltmeter just has a ton of resistance. And before the switch is closed, we basically have two circuits. We basically have circuit 1 where the battery goes and the current goes like this, and then we have circuit 2 where the current goes like this. So you wouldn't really have any current flowing between the two batteries. We basically have two circuits. Once the switch is closed, then current in this battery could also flow to the right. So therefore, some of the current in this battery would flow to the right. Most of it would still flow to the left. However, the current flowing through the voltmeter would be decreased. So therefore, the reading of the voltmeter would also be decreased, because the current is lower, and since the resistance stays the same, then the voltage must decrease. So the answer is C. To question 16, the answer is C. Question 17 shouldn't be too hard. In the circuit shown, R1 has a resistance of 6 ohms, R2 has a resistance of 3 ohms, and the EMF of the battery is 30 volts. The reading of the ammeter is most nearly what? Well, so since these two resistors are in parallel, we are going to calculate their equivalent resistance, which is 1 over 6 ohms plus 1 over 3 ohms. That is equal to 2, so the equivalent resistance of the two resistors is equal to 2 ohms. Now voltage equals current times resistance, so 30 is equal to 2, the resistance, times I, the current. And therefore I equals 15, the current is equal to 15 amps. So now you know that the current across the current is 15 amps across the battery, but you know that the current is splits up at this junction. So since the current is splits up at this junction between R2 and R1, we need to further calculate. Now the current is splits up at this junction between R1 and R2, and you're only worried about the current going through R1 because that's where the ammeter is placed. The ammeter is placed where the current is going through R1. So how do you know this? Well, this is where Kirchhoff's loop rule comes into place. The voltage across a loop, the total change in voltage across a loop has to be 0. So therefore the change in voltage across the battery and the change in voltage across the resistor have to be equal. And the change in voltage across the battery has to also be equal to the change in voltage of this resistor. So we can take V1 and V2 and say they are equal. Now, and they're both equal to 30 volts. Now 30 volts is equivalent to the current traveling through resistor 2 times the resistance of resistor 2. Remember that voltage is equal to current times resistance. So 30 volts is equal to the resistance of resistor 2 times current of resistor 2. And it's also equal to the resistance of resistor 1 times the current of resistor 1. So 30 is equal to them, and if you set them equal to each other, then you will find that, like, if you set them equal to each other and like do all the math, you'll find that the current 2, the current traveling through resistor 2 has to be 10 amps. So therefore current 1 is equal to the current here, which is 15 amps, minus the current flowing through R2, which is 10 amps, so you end up getting 5 amps. So the answer to question 17 is C, 5 amps. Now I'll give you 20 seconds to read over questions 18 and 19, and also keep in mind that if you ever feel like 20 seconds isn't enough, you can always pause the video. So yeah. Excuse me about that, I was just drinking water. People drink water. Anyway, so which of the following is true about the direction of the magnetic field produced by the current at the position of the electron? Well, this requires you to know the right-hand curl rule, which is the rule that determines what direction the magnetic field is in. Now, so as I said, you point your thumb in the direction of the current, and then the way in which your fingers bend is the direction of the magnetic field. So if you point your thumb in the direction of this current, and keep in mind this is your right hand, not your left hand. If you point your thumb if you point your thumb of your right hand to the right, then your fingers would curl like this. Your fingers would curl like this, and therefore at this exact point, your fingers would be pointing downwards. So therefore the magnetic field produced by the current at this position would be down. Like what I mean by down is like into the page. Yeah, that's what I meant. Sorry, not down. It would be into the page. So the answer to question 18 is D. And the answer to question 19 is E, because there is no direction. Remember that the magnitude of the magnetic force is 0, because there is, like, how do I say this? Because, like, there is no movement of the electron. So, like, yeah, there is no movement of the electron. It says it right here. The electron is released from rest. Since the electron isn't moving in the first place, there must be no magnetic force. So the direction of the initial magnetic force is 0. Anyways, questions 20 to 22 go together. I'll give you 20 seconds to read over them, and I'll go over the answer. Okay, so 20 seconds have passed, so I'm gonna go over the answer now. Basically, the ratio of QC to QB, what is the ratio? Well, now the electric force of charges is equivalent to K, which is 1 over 4 pi epsilon naught. Anyway, so it's equal to K times the charge of the two charges, times the charge of the two charges, times the charge of, times the charge of charge 1, times charge of charge 2. All of that over r squared, r being the distance. Now, since it says that the net force on sphere A is 0, since the net force on sphere A is 0, that means the electric force produced by charge B and the electric force produced by charge C have to be equal. So we can set them equal to each other, and then we end up solving for QC over QB, and we end up getting 9 over 4. QC over QB is equal to 9 over 4, so that must be the ratio of the charges. Now the answer to question 21 is D, because they must have different signs. And the reason why is because the QB and the QC both, QC and the QB are both to the right of QA. They are both to the right of QA, and their forces cancel out. Since they are both to the right of QA, and since their forces cancel out, that means their forces must have opposite charges. And since their forces must have opposite charges, that means they must have different signs. Yeah. So answer is D. Now, question 22 asks, which of the following is true about the sign of charge QA? Well, we don't know. It is possible that QA could be either positive or negative. It's possible for either. Like, we don't know. Nowhere in the question does it specify what charge they have to be. They can be any charge. So, yeah, the answer to question 22 is E. And also, if you look through answers A, B, C, and D, none of them have to be true. So we know that the answer is E. Question 23 is a really hard question. I'll give you 20 seconds to read over it, and I'll go over the answer. Anyway, I'm back. So question 23 is pretty hard. It requires you to understand Kirchhoff's loop rule as well as the junction rule. So the junction rule states that the current flowing into a junction has to be equal to the current flowing out of the junction. So that means we know that the current flowing in here must be equal to the current flowing out of here, which are both here and here. Now I'm gonna redraw this diagram, but with more labels so that you know what I'm talking about. So the current flowing from here to here, let's call that N0. The current flowing from here to here, let's call that N1. The current flowing from here to here, let's call that N2. The current flowing from here to here, let's call that N3. And yeah. Now, according to the junction rule, we know that N0 has to be equal to I plus N1 because, the current flowing into the junction must equal to the current flowing out of it. And we know that the current N0 also has to be equal to the current flowing here. And the current here is the current flowing from here to here is N3 plus 2I, because, N3 plus 2I, that's the current here. All right. Now, we also know that the current 2I equals, so 2I here, the current for 2I here has to be equal to N1 plus N2, because current N1 flows into here, current N2 also flows here. So the current 2I must equal to N1 plus N2. And I is also equal to N3 plus N2 because because the current flowing here is I, the current flowing into the junction here is I, and the current flowing out of this junction is N2 plus N3. Now we are going to take Kirchhoff's loop rule. Oh yeah, one thing that you probably are wondering is, how do we know that the current must flow from here down here? Can't the current also flow like this? How do we know? So this is a legitimate question. This is a legitimate question. How do we know that a current is flowing like this, down R? Why can't the current flow up R? Well, to answer your question, the answer to that question is the resistance here is greater than the resistance here. And also because if you assume the current is flowing up like this, then the rest of our equations wouldn't make sense. So yeah, so that's how you know the current is flowing down. I mean if you assume the current is flowing up, then you get a negative current, so I guess that also makes sense. But you'll get a negative current once you solve all the equations. So yeah, we know that the current has to flow downward. Now, according to Kirchhoff's loop rule, we know that the induced EMF, so this loop, let's take this loop. Now in this loop you have the EMF, sorry, not induced EMF. You have the EMF of the battery, and the EMF goes through the resistor 2R and goes back here. So EMF, the EMF of the battery minus the voltage across this battery has to be equal to 0. Now the current can also flow like this in this loop. So this has to also be equal to 0. It can also flow like this in this loop. So all of these equal to 0. Therefore, we know that EMF is equal to 2R and 3. EMF is also equal to R and 2. EMF is also equal to X and 1. So we can set all of them equal to one another, to each other. And now we're going to do a little algebra. So we know that I plus N1 is equal to 2I plus N3. We subtract I from both sides. We multiply 2 to both sides. And here we have 2I. We have 2N1 equals 2I plus 2N3. We know that 2I is equivalent to N1 plus N2, so we can substitute that in. So we have 2N1 equals N1 plus N2 plus N3. All right. So now we subtract N1 from both sides, and we get N1 equals N2 plus 2N3. And now we're going to multiply R to both sides, which is resistance. So we're going to get voltages here. Right here we have currents, but now we're going to have voltages. Rn1 equals Rn2 plus 2Rn3. So now we know that Rn2 is equivalent to 2Rn3 and is also equivalent to Xn1. So we can substitute Xn1 in for Rn2 and 2Rn3. So we get Rn1 equals Xn1 plus Xn1. and then we say that that is equal to 2x in 1, and then we divide both sides by 2 in 1, and we get r over 2 equals x. So the answer to question 23 is equal to C, because x, the resistance of x, is r over 2. Questions 24 through 25, I'll give you 20 seconds to read over them, and I'll go over the answer. Alright, I'm gonna go over the answer now. So, what really is gonna confuse people is the capacitor. Now, the capacitor behaves like regular wire when it is uncharged, and a capacitor behaves like so an uncharged capacitor behaves like regular wire, and a fully charged capacitor behaves like an open switch. So now, what is the current in the 10 ohm resistor immediately after the switch is closed? Well, immediately after the switch is closed, the capacitor behaves like an open wire, so we can just think of this as an open wire. And yeah, so therefore we can just assume that assuming that imagining the capacitor as an open wire, we know that the resistance across the equivalent resistance would just be 10 ohms, because if we imagine the capacitor as an open wire, then that means we imagine there's zero resistance going here, so the equivalent so therefore no current would flow through the 20 ohm resistor, or the current would flow through here. So the resistance is 10 ohms, and since the voltage is 30, and since the resistor is 10 ohms, V equals IR, therefore I must be equal to 3, so the current is 3 amps right after the switch is closed. So the answer to 24 is D, 3 amps. Now for question 25, it asks what is the current in the resistor a long time after the switch is closed. So a long time after the switch is closed, the capacitor would be fully charged, and a fully charged capacitor behaves like an open switch. So therefore we would just imagine that current would no longer go through here. Instead, current would only go through here, and therefore the equivalent resistance would be equal to the resistance of these two resistors added together, because they're in series. So the equivalent resistance is 30 ohms, and then we take the V equals IR equation, and we end up getting the current is equal to 1 amps. So the answer to question 25 is B, 1 amp. I'll give you 20 seconds to read through this, and I'll go for the answer. Alright, so now how do I say this? So Q equals CV, charge equals capacitance times the voltage. Now the capacitance decreases by half because the distance between the two plates is doubled. Keep in mind that when the distance between the two plates of the capacitor doubles, the capacitance decreases by half, because the formula for capacitance is K times area over distance. Times that thing. Anyway, so since the capacitance decreases by half, and since the voltage remains constant, then the charge also has to decrease by half in order for Q equals CV to remain true. The reason why the voltage remains constant is because it is still connected to the battery. Since it is still connected to the battery, the voltage must remain constant. Yeah. So therefore the new charge on the capacitor would decrease by half, so it must be either D or E. And now we're gonna use the equation for potential energy. The equation for potential energy is also on your formula sheet. It's equal to 1/2 times Q delta V. So yeah. So since delta V remains the same and since Q decreases by half, then the potential energy must also decrease by half. So the correct answer is E. I'll give you 20 seconds to read through this problem and I'll go over the answer. Alright, so this one is pretty self-explanatory. I don't think it requires much explaining to do. The answer is C for both of them. It's upside down, I don't know why, but like, you know, the answer is C because like the inner sphere has a total net charge of minus Q and the outer sphere has a net charge of a plus 3Q. Since the outer sphere has a net charge of a plus 3Q, that means the charge in the inner surface and the charge in the outer surface have to add up to plus 3Q. Like, yeah, the charge at the inner surface and the charge at the outer surface have to add up to plus 3Q. And like, you know, the answer to this question is pretty self-explanatory. I don't think I need to go into detail. Both of them are equal to C. The answer to question 27 is plus Q and 28 is plus 2Q. Q and plus 2Q add up to plus 3Q, which is the net charge. And I think it's pretty self-explanatory. I don't need to like go over why. So next question. Questions 29 through 30. I'll give you 20 seconds to read over the questions and then I'll go over the answer. Alright, so at which of the labeled points does the electric field point towards the right with the smallest magnitude? Now you probably know how electric fields point. They point away from positive charges and they point towards negative charges. So the electric field would point this direction. Now, how do we know the magnitude? Well, the magnitude of the electric field would just be the magnitude of each charge over the distance squared. So the electric field at point... Now we know that the electric field at point A cannot be the correct answer. A cannot be correct because A points towards the left. And the reason why A points towards the left is because like this plus 4Q is greater in magnitude than the minus 3Q, and like it points towards the left. So A cannot be correct. So therefore it's either B, C, D, or E. Now, we know that E cannot be correct because if we solve for the electric field at point E, we'll see that it's less than 0. And since it is less than 0, it's negative, meaning that it points towards the left. But it cannot point towards the left because it only points towards the right with the smallest magnitude. So therefore it must be either B, C, or D. Now therefore we just calculate the electric field, the magnitude of the electric field at points C, B, and D, and we find that the one with which the magnitude of the electric field is the smallest is point C. So the correct answer to question 29 is C. Now for question 30, at which of the labeled points does the electric potential have the highest positive value? This would be obviously A, because, so one, we need to look at how far away they are from the negative charge. Basically, the closer you are to a negative charge, the lower the electric potential is, and the closer you are to a positive charge, the higher the electric potential is. So A and B are the closest to the positive charge, and A is the farthest from the negative charge, so the answer to question 30 has to be A. Now for question 31, object A and object B are separated by distance d. Object A has charge plus q and object B has charge minus 2q. Object A has a force of magnitude F exerted on it by object B. What are the magnitude and direction of the force exerted on object B? Well, Newton's third law of motion is that every force has an equal and opposite reaction. Every force has an equal and opposite counterforce. But that's not relevant. What's relevant here, well, okay, that kind of is relevant, but what's actually relevant here is that when there are two charges, regardless of what the two charges are, the force that one charge exerts on the other charge has to be equal in magnitude to the force that the other charge exerts on the first charge, and they point in opposite directions. So the answer to this question has to be D. Because since the two charges are different in sign, since one charge is positive and since the other charge is negative, they have opposite signs. So therefore they must point, the forces that they exert on each other must point towards each other. And they must be the same. So the answer is D. For question 32, I'll give you 20 seconds to think and then I'll give you the answer. Alright, so now in this problem the voltage is given in terms of time and beta is a constant. Now remember that you have your formula sheet, alright? You have a formula sheet and the formula sheet is very important because, I mean, of course you could memorize the formulae, but like having it definitely helps. So the EMF is equal to negative L times di dt. Now L stands for inductance, like L is inductance. So now EMF, we can just, in the context of this problem, EMF is just voltage. Yeah, in the context of this problem, EMF is just voltage, and voltage is equal to beta t squared, so we can say that beta t squared is equal to inductance di dt. Now we're going to take the integral of both sides with respect to t. After we take the integral of both sides with respect to t, the right-hand side just gets rid of the di dt and you just get Li. Well, I guess you could say it's negative, but like, yeah. So like the integral with respect, taking the integral with respect to time gets rid of the di dt and gives you just I and then Li. Then the integral of the left-hand side is equal to beta t cubed over 3. If you're not too familiar with calculus, to take the integral of t squared, the integral of t squared dt is equal to t cubed over 3, and then you multiply by beta, which is a constant. And then you divide both sides by L, the inductance, and you get beta t cubed over 3L is equal to I, which is the current. I is current. And the negative sign, you get rid of the negative because the negative gets getting rid of. Anyway, so therefore the answer is D. So the answer to question 32 is D. Yeah. Now for question 33, I'll give you 20 seconds to read over and think, and I'll give you the answer. So the answer to question 33, you need to know the curl right-hand rule, and you also need to know the right-hand rule regarding the magnetic force. So induced current. So okay, so first of all, the magnetic field is decreasing. Like at time t equals 6, the magnetic field is decreasing and going from positive to negative. and the induced current. So one good way to remember this is that the induced current has to counteract the change in magnetic field. That is how induced current works. So since the magnetic field, since the change in magnetic field, since the magnetic field is going from positive to negative, therefore the change in magnetic field points into the page. So therefore the induced current would create a magnetic field that counteracts the change in magnetic field. So the induced current would point out of the page. So therefore the induced current must be clockwise. The reason why is because if you point, so at this point, if you use the curl right-handed rule, you'll see that when you point your thumb upwards, then the induced current would be out of the page, which counteracts the change in magnetic field. I mean, sorry, not induced current, the magnetic field of the current. And if you go here, if you point your thumb to the left, then your fingers would also curl out of the page at the center. So basically a current flowing counterclockwise would produce a magnetic field that points out of the page. So therefore the current's direction has to be counterclockwise. And we know that the answer has to be either B or D, because like these are the two counterclockwise answers. And you could just use intuition to guess this one, that it's D, because the magnitude cannot possibly be that high for question B. I mean, answer B. Answer B says that the magnitude is 3.8, but like it cannot possibly be that high, because the change in magnetic field, the change in the magnetic field is like very small. It's like the slope of this line from 3 to 6 is a negative 0.4 over 3. So like 0.4 over 3. So like basically the change in magnetic field is so small that the magnitude of the current, of the induced current, cannot possibly be 3.8. So it has to be D. Since we know that the direction has to be counterclockwise and it cannot be that high, the answer choice is D. You could also use some equations, the equations given to you by the formula sheet, but like you really don't need that. You can, yeah. Now question 34 is pretty simple. A negatively charged ion is moving towards the top of the page when it enters a region of space with a uniform magnetic field B directed to the right as shown above. The direction of the force that the magnetic field exerts on the ion is O. Now, however, you also have to know that the ion is negatively charged. Since it is negatively charged, therefore it basically means current is going downwards. So because current is in the opposite direction of the movement of negatively charged particles. Current is in the opposite direction of the negatively charged particles. So therefore you have to point your thumb downwards and your fingers to the right, and then your palm would point out of the page. So the answer is D. Question 35, I'll give you 20 seconds to think and I'll go over the answer. Alright, so what is the answer? Well, again, you use the right-handed rule for magnetic force. Remember that your thumb points in the direction of the current, your fingers point in the direction of the magnetic field, and your palm would point in the direction of the force. So now you would point your fingers into the page, because that is the direction of the magnetic field. And you would, for segment 1, you would point your thumb to the left. So yeah, for segment 1, you would point your thumb to the left, because that's the direction of the current. And then you'll see that your palm is pointing downwards, so the direction of the magnetic force of a segment 1 has to be towards the bottom of the page, downwards. And also the magnetic force of segment 1 and segment 2 would be the same, so therefore the answer to question 35 is A. The magnetic force of segment 1 and segment 2 are the same. Now this may sound like, it may sound wrong, because segment 2 is much longer than segment 1. However, you're only looking at the part of segment 2 that points towards the right. The amount with which segment 2 points towards the right is the same as the amount with which segment 1 points towards the left. So therefore the magnitude of the magnetic force of segments 1 and 2 have to be the same. And I understand that there is some part, like at this point in segment 2, the magnetic force points this way, so I understand that at this point the magnetic force points towards the left, and at this point the magnetic force points towards the right, but the magnetic force pointing towards the right and the force pointing towards the left cancel out to only give you magnetic force pointing upwards towards the top of the page. So yeah, the answer to question 35 is A. Anyways, this is it for the multiple choice section of the AP Physics C Electricity and Magnetism exam for 2017. This is the end of the multiple choice section. Thank you for watching my AP Physics C, E&M walkthrough/tutorial. I hope my video helped you prepare for your AP exam. If so, be sure to hit the like button, subscribe to my channel, and hit the bell icon to never miss another upload. And if you have any lingering questions, feel free to leave a comment asking me anything. I will respond as quickly as possible. And yeah, for those of you who know my channel well, I know I am deviating from my usual videos. I usually post memes and gaming, and this is because I am experimenting with different types of videos to see if I can get more views, and if my study tutorial videos do well, I'll upload more tutorial videos. And last but not least, if you're new to my channel, feel free to check out my gaming and meme videos as well. This has been Charlie. Thank you so much for watching. Please hit the like button if this video helped, leave a comment, and subscribe to my channel, and share this video with all of your friends. But anyways, this has been Charlie. Until next time, take care.